Good afternoon. Welcome to the CERIAS Security Seminar. It's my great pleasure to introduce today's speaker, Professor Matthias Peyer, who joined the Computer Science Department as a faculty member last year. He received his PhD from ETH, and before joining Purdue, he was a postdoc at UC Berkeley, and his research interests are in software security, especially all kinds of topics in software security, especially binary security. And today he will talk about the code pointer integrity.
Hi, thanks for the introduction. Hi folks, the work I'm going to present today is joint work with Volodymyr Kuznetsov, Laszlo Shekeres, George Kandea, R. Shekhar, and Don Songs, while most of the people were at Berkeley and different places in between. Most of the awesome work and implementation work has been done by the students, so all credit goes to them. All the bad jokes are my fault. So let me start with the reality that we are facing as security researchers and programmers every day. It is an ugly planet out there. It is a bug planet. There are way too many bugs in software out there, and there's no way we're going to be able to fix all of them. While finding and fixing bugs and vulnerabilities is important, it unfortunately does not scale, and we will never be able to find all the vulnerabilities that are out there. And there's always that one weird big bug lurking behind us, waiting to catch us unaware. Also, we are focusing on memory corruption, and memory corruption is abundant. It's everywhere. If we just look at the last couple of years and we look at the security vulnerabilities that were published as CVEs, just in the area of control flow hijack attacks, we see that there's a huge amount of these vulnerabilities that allow attackers to actually completely control your software and your computer. So starting in 2004, the average amount of control flow hijack attacks was continuously increasing until the right-hand side of the figure for 2013. And we just picked a couple of software pieces. So one of them is Acrobat, that many people use to display PDF software. It's full of vulnerabilities. But also browsers like Firefox or Internet Explorer have had a large amount of these vulnerabilities that allowed an attacker to compromise your software security. But also operating systems like OS X and Linux had a couple of failures that allowed people to exploit them and attack your software systems. So it actually looks like as if we are being overrun by all these bugs that are out there, and there's no way how we can protect ourselves against them. We have this little fortress of protection where we're trying to write safe code, but there are just too many bugs creeping in. And if we just look what happened in the last couple of months, there was Heartbleed, which allowed people to read all bunch of private data from our computing systems. There was Shell Shock, which allowed arbitrary command execution on a huge amount of servers. And there are still many embedded systems out there that are not patched against this vulnerability. And also more recently, there was the Ghost vulnerability, which allowed people to arbitrarily corrupt data in processes by controlling a couple of DNS queries, and allowed them to then exploit and get to arbitrary code execution. So at the basis of all these vulnerability, there's the simple memory safety violation. And let's look at what a memory safety violation is. It all starts with a form of invalid dereference. So we are doing some kind of pointer manipulation and reading from some part of memory that we shouldn't read. So something goes wrong when we dereference a pointer. And it can either be a dangling pointer, which is a temporal memory safety violation, where a pointer initially pointed to a valid object, but then that object was deallocated or returned with a free. But the pointer itself was not removed or zeroed out. And while keeping this pointer around is perfectly safe, accessing the pointer leads to a memory safety violation. And the second kind of memory safety violations are out-of-bounds pointers, which are spatial kind of safety validations. So initially, the pointer points to a valid object, and due to some pointer computation, the pointer is moved along. For example, if you're walking through an array step by step, and you're incrementing the pointer past the array, this is an out-of-bounds violation, where you're suddenly accessing data that is no longer in bounds, and thereby it results in a memory safety violation. So it is only an actual violation if the actual invalid pointer is read, written, or freed again. So as long as the pointer just remains in the program and we are not using it, everything is safe, according to the C and C++ language semantics. But as soon as we dereference or use that pointer for some other computation, the memory corruption actually happens. So when looking at defense mechanisms, we always have to define a threat model. And the threat model we are using for this talk is as follows. We assume a very powerful attacker model in that the attacker can read and write arbitrary data. So all the data on a heap, on a stack, or in any global place is allowed to be read by the attacker. And the attacker can also read the code. So the attacker can try to learn secrets from the code. What the attacker cannot do is modify the program code. So the attacker cannot inject new code. And also the attacker cannot influence program loading. So this is actually a very realistic attacker model, because if you assume generic memory safety violations, that's exactly what the attacker can do. And if you're working in a multi-threaded environment, so just imagine the Apache process spawning a couple of worker threads, you can repeat the memory safety violation and thereby get arbitrary memory access and read and write the complete memory space of the application and thereby compromise it or set up the attack that you actually want to carry out. So the control flow hijack attacks that we are actually talking about looks as follows. Here's a simple piece of C-like code that we are looking at as a motivating example. In the first line, we're defining a function pointer that is later used at the end of the program. And there's some computation between the definition of the function pointer and the actual use of the function pointer. So there's some pointer queue that we assign from a valid buffer plus some attacker-controlled input. After that, at one point in time, we assign the function pointer, but later on, there's some additional manipulation of the pointer queue, which is the second attacker-controlled value. So in a control flow hijack attack, the attacker can use these abstract steps to actually get control over the executed application by initially redirecting the pointer from the valid location. So initially the pointer or the programmer intended Q to always point into the buffer, but by supplying additional values, the attacker can make the pointer point into to the function pointer itself. So the attacker has to know the correct offset as a first step of attack. And as a second step of an attack, the attacker overwrites the function pointer to an attacker-controlled gadget, which will then be used to exploit the behavior and redirect the control flow of the application to an attacker-intended gadget. And as a third step, the function pointer is actually must be used by the application. Only then will it actually be dereferenced and the bad stuff happens. So what about existing defenses that are out there? What do we have to protect our software against these kind of vulnerabilities? So for one, there's data execution prevention, which was introduced in 2006, which roughly protects against code injection attack. So before that, before data execution prevention, attackers were able to inject new executable code into processes and then execute that code by redirecting the control flow to that injected code. So data execution prevention added a couple of bits in hardware to protect against this and keeps additional state if a memory page contains either code or data, and allows us to distinguish between code and data and protects against all code injection attacks. But code reuse attacks still remain, and there's some additional protection on top of it. So there's address-based layout randomization that is a probabilistic defense that shuffles the memory areas or memory segments that are used in the process every time a process is started. So this protects against some form of pre-compiled locations and where the attacker knows where the current location is. So the attacker first needs an information leak to recover the actual pointers and then use those in a second step of the attack. And last but not least, we have stack canaries, which are another probabilistic defense mechanism that protects the stack against continuous buffer overrides, buffer overflows on the stack frames. Unfortunately, as we've seen before in the motivational slide, all of these defenses can be mitigated, and there are many ways around it. If you would like to know more about this, there's an earlier CERIAS talk about all the different steps of a software attack, and there are some nice papers out there as well that I reference. So you might say, memory safety to the rescue, right? If we just move away from these unsafe languages like C and C++ and implement all our software in safe languages, we'll be safe, right? So people proposed a large set of safe languages. So there's Python, there's Java, there's C#, and there's Swift, right? So we've solved the problem. Now, while these languages themselves enforce memory safety for a program and do not allow an attacker to gain code execution capabilities, there's a slight caveat that we have to look at. So let's look at a specific example. When we look at Dropbox, Dropbox has a small component that runs on your system that is implemented in roughly 3,000 lines of code to download files and synchronize files. So it's like 3,000 lines of memory-safe language, right? So nothing can ever happen, or no memory safety violation can ever happen while executing this code, right? So while these 3,000 lines of code are safe, there's more software beneath it on the stack. And the Python runtime is implemented in 500 lines of code. Guess what? C code, right? Which can be full of memory bugs, and there have been several vulnerabilities in there. But it doesn't end there, right? Below the Python runtime, there's the C library, which has roughly 2.5 million lines of code, all implemented in C. And the Ghost vulnerability was a prime example that these libraries are still full of bugs, and bugs that have not been found in the last 15 years. But if you go deeper than that, there's also the Linux kernel of roughly, that consists of roughly 60 million lines of C code. So while we do have some memory-safe languages, the majority of software that we are running on current systems has been implemented on top of C or C++. So while memory-safe languages are a goal and we would like to get there, we are unfortunately not yet there. And there's a large part of the code that remains unsafe. So if you look at this, yeah.
So I wonder which of the defense mechanisms are deployed at the kernel? You mentioned the three defense mechanisms.
The kernel has ASLR, so okay. The kernel uses some form of address space layout randomization, and data execution prevention. Unfortunately, data execution prevention can be mitigated in most kernels because the kernel, in kernel space, the attacker has access to raw memory. And one approach could be you just set the flag that your page is executable by using a memory safety attack. Or there are some other ways around that as well by changing some data structures and so on. Yeah, good question though. So memory safe languages are where we would like to go to, but unfortunately we are far off. It takes us a long way from where we actually are to implement our systems in safe languages. So what can we do? Well, we can try to retrofit memory safety on top of these existing languages to protect the huge amount of legacy code that is out there. So several systems have been proposed to retrofit memory safety on top of C and C++. So there has been softbound and CTS, which is roughly 116% overhead if you run it on software. There's secured, which has lower overhead, but comes with an additional cost of rewriting software or that it doesn't work for all the software. And there's address sanitizer, which has lower overhead than softbound and CTS, but comes at an additional restriction of unsoundness, where it doesn't find all the bugs and is restricted in its practicality in some ways. But let's keep the idea of retrofitting memory safety around, and let's see how memory safety would actually work, how you would retrofit memory safety on top of these systems. So again, we look at a simple program, and it's basically the same program as before without the function pointer. So we first allocate that buffer and then manipulate a pointer to that buffer using some attacker-controlled input, and then assign a value to that pointer that the attacker has control of. So how can we protect these kind of pointer accesses? Well, memory safety explicitly adds additional bounds checks to all the pointers that allow some runtime checking that the pointer dereference is actually valid at the time. So in addition to the buffer pointer, we add lower and upper bound variables to the actual code that is executed and initialize it when the pointer itself is initialized and assigned. In addition to that, whenever the pointer is changed, we propagate metadata to the pointer. So the pointer Q is updated as well with the pointer metadata of the buffer. And later on, if there's an access to the pointer, before that access, we add an additional check to ensure that the pointer is still in bounds. If the pointer is no longer in bounds, we abort the program with a memory error. So what we actually end up with is some form of safe program that allows the runtime detection of memory safety vulnerabilities. But unfortunately, it comes at a very high price, and we are paying 116% performance overhead, which is a nice proof of concept, but people will not use it in practice. So we have to work towards lowering this overhead to make it actually feasible to use it as a defense mechanism, even on current systems. The problem that we are currently facing with these defense mechanisms is that even though we have built a couple of nice forts, we are always faced with the safety versus flexibility and performance question. So either we get safety on one hand, or we get flexibility and performance, but we cannot get both. Yeah.
So would the previous defense break some C code? Is it possible that?
Which ones?
The one you just showed by adding the boundary check, propagating the boundary. Is it possible that some complicated code?
Yeah, it is. While softbound is mostly safe and supports most of the code, it does rely on inferring some form of type system and type dereference. So there's always some restriction in VR cases where it will not work out. Yeah, good question. So we are faced with that question. And still, if you would like to know more about softbound, or the safe defense mechanisms, there's been a nice talk that you can watch, or you can read about softbound, ASAN, and Secure by just looking at the papers. So we now know that the current defense mechanisms are not effective. Memory safety would be nice to have, but comes at a too high overhead. So we're looking at a new approach. Keep in mind that we would like to have memory safety, but it is too expensive to enforce it for all the data. So let's just move forward and only select a subset of data that we're actually interested in protecting. So instead of protecting the complete heap and all the stack, or all the stacks actually if you're running multiple threads, we only protect a subset of the data. All the code pointers that are actually used in the heap or on the stack, by pushing stuff on a safe copy of the stack, thereby enforcing the integrity of the data, but only a subset of the data that we are actually interested in. So we offer a strong protection for a select and well-defined subset of data, instead of offering full protection for all the data that is out there. The attacker may modify any of the unprotected data, and we don't give any guarantees whatsoever about the remaining data that is out there. So the attacker is free to run any data-only attack on top of the other data that is not protected. So instead of protecting everything a little, we protect a little as good as we can, offering strong integrity guarantees. And to give you a peek into the performance that we are looking at, if we are running full memory safety, we are faced with these 116% overhead. But if we protect only code pointers and give strong guarantees for all the code pointers that are used in the program, we can protect against control flow hijack attacks at low 2 to 8.4% performance overhead. These two numbers are two different policies that we implement, and we will go into more details what the different policies entail later on. So these two policies offer strong protection against any software attacks by protecting only the code pointers and not giving guarantees about any other data that is in memory. So let's start with code pointer separation, the first security policy. Instead of just having one heap, we logically separate the heap into two pieces and look at the regular heap for the program and any safe pointer on top of it. So we do have regular memory where all the unprotected data remains, and we do have safe memory, or we introduce safe memory as well, where we move all our function pointers to. And we thereby separate or logically separate function pointers and any remaining data, and taking the option or the possibility of an attacker to modify it. So the safe memory contains code pointers only and nothing else, while the regular memory contains all other data. So the function pointers are moved to the safe memory, and there's just a placeholder that remains in the unsafe memory. The memory layout is unchanged to allow binary compatibility with unprotected libraries. While we do not give any guarantees of code that is running in unprotected libraries, we do allow the code to be run. And an unchanged memory layout allows us to actually do that. On the control plane side, any value is either a code pointer or null. And we enforce that any pointer, any code pointer, can only read and write from the safe memory area. So the only thing we can read are other code pointers or null. And thereby we restrict the set of values that can be written in the safe memory to the code pointers only. In addition to the protection on the heap, we also have to offer protection of the actual stack frames to protect against any stack-based overflows. And there were several ideas that we looked at, including shadow stacks and other defense mechanisms. But most of them resulted in 5 to 8% overhead. And we wanted to achieve much lower overhead in practice. So what we came up with was a separation of stack frames into safe and unsafe stack frames, or safe and regular stack frames. On the regular stack, we have all the values that are used for pointer computations or for other computations. And on the safe stack, we have all the values and variables that we can prove safe. So everything that's accessed safely, or that we can prove in our compiler pass that is safe, is pushed to the safe stack. And anything else, like anything that uses weird pointer accesses or that we cannot prove is safe, is pushed to the regular stack. We don't give any guarantees whatsoever for data on the regular stack. So any array might corrupt any other array. For the sample program that we're looking at here, the safe variables are R and the return address, the code pointer, and the unsafe variable is the buffer itself, because there could actually be a buffer overflow happening. So to summarize, how does the memory layout actually look like? Again, we have split the memory of a program conceptually and logically into two planes, the safe memory area and the regular memory area. In the safe memory area, all memory accesses are safe. In regular memory, all memory accesses are fast. And we actually use hardware-based instruction level isolation to separate these two memory areas, using already existing features available on current architectures. So the regular memory contains regular heap, stacks, and code, which is mapped read-only and cannot be modified by the attacker in that case. And the safe memory contains the safe heap that only contains null values or pointer values or values for function pointers, and the safe stacks that contain all the safe data on the stacks. So given this separation, how can we still attack code pointer separation? So one single example would be that an attacker can reuse existing code pointers out of context. We do know that the attacker cannot forge a new code pointer by pointing it to some arbitrary location, but an attacker might reuse a code pointer. And let me illustrate that with an example. So in this example, we have our function pointer again and our motivating example, but the function pointer is assigned through a struct, and the attacker again has control over our pointer queue and can set the memory location and the actual value that is used. So we do know that the attacker cannot modify the function pointer itself. But what the attacker can modify is the dereference from the struct pointer to the actual function pointer, and thereby going through the indirection. So the attacker can modify the structure pointer from pointing to the beginning of the struct to some other copy of the struct that is somewhere in memory and contains another valid function pointer. So the struct that the attacker constructs actually must contain a valid function pointer. Otherwise, the value in the safe memory would be null and the program would stop when it is dereferenced. This way, an attacker can replace one function pointer with another function pointer by going through a dereference chain from a struct. So the other value must be null or a pointer to another function, as I said before. How do we do that? We identify all code pointer accesses through a compiler pass that looks at a type-based analysis and identifies all the code pointers. We separate those identified types using instruction level isolation. For x86, this would be segmentation. And the CPS code pointer separation gives you a couple of security guarantees. Most importantly, an attacker cannot forge new code pointers. So an attacker can only reuse the code pointers that already exist in the safe memory area. Code pointer is either an immediate, as encoded in the instruction itself, or assigned from another code pointer. There cannot be any attacker-controlled or attacker-constructed code pointers in that safe memory area. The capabilities that remain to the attacker are that the attacker can replace existing functions through indirection. So for example, going from foo to bar to func, the attacker can redirect it to foo bus func2 and thereby control it. But func2 must still be a valid pointer. So in practice, we've grouped our code pointers together and can thereby protect them against any attacks from the outside by keeping them in a safe area and ensure that there are no outside accesses. But we can do better than that. So building on top of code pointer separation, we introduced code pointer integrity as well. So the set of the sensitive pointers that we are protecting is now no longer just the code pointers, but code pointers and pointers used to access sensitive pointers. So this is basically a transitive closure on all the pointers that are used to directly or indirectly access any code pointer. Again, we rely on identifying sensitive pointers using an over-approximate type-based analysis. So the over-approximation tells us that it will always be safe. In the worst case, we'll protect additional data that we wouldn't need to protect, but will be safe in any way. There might be additional overhead, but we can still ensure safety. So the over-approximation only affects performance. We measured on SPAC CPU that less than 6.5% of all the accesses are sensitive, according to this definition. And compared to softbound, we only have to protect 6.5% of the memory accesses, which gives us a big performance speedup. So how can we attack code pointer integrity? We have the same example as before, and let's see what additional instrumentation is actually automatically inserted. So we do have the lower and upper bounds of the pointer, and we do run the bounds check before the pointer is actually accessed, and the attacker can redirect the structure to an attacker-controlled value. And in this case, there will actually be an exception when the attacker-controlled value of Q is dereferenced, and we can stop the program before the actual memory safety corruption or memory safety violation happens, and thereby protect the integrity of the system. So to make the difference between code pointer integrity and code pointer separation explicit, let me quickly highlight the main difference. Both systems separate sensitive pointers from regular data and push all the sensitive data to a safe memory area. Both of them rely on a type-based static analysis, but the set of sensitive pointers is defined differently. For code pointer integrity, it is code pointers and all pointers to sensitive pointers. For code pointer separations, it's code pointers only. Accessing sensitive pointers is always safe. So for code pointer separation, we do have separation of the code pointers into its own memory area. But for code pointer integrity, we extend the separation with additional runtime bounds checks that ensures that no other value can be used to overwrite any pointer in the dereference chain. And accessing regular data is fast. So any data that we don't protect can be accessed at regular speed without any additional overhead or any additional instrumentation that must be executed on top of it. So you might wonder, what kind of security guarantees do we actually give? For code pointer integrity, we have a formally guaranteed protection where we guarantee memory safety for all the code pointers. So the code pointers can never be modified by a memory safety violation using this approach. This results in 8.4% overhead for spec and 10.5% overhead for the Phoronix benchmarks. And we are protecting roughly 6.5% of all the memory accesses. This is low overhead that can be actually used in practice, but we would obviously like to see something that's lower than that or even lower than that. Therefore, code pointer separation offers strong protection in practice and allows you to separate all the code pointers from any attacker-controlled value and prohibits attackers from forging code pointers. In practice, we see 0.5 to 1.9% overhead, and we are protecting roughly 2.5% of the memory accesses. Something that I only touched briefly is the safe stack, which offers you full protection against return-oriented programming if you only deploy the safe stack itself. And I'm only mentioning it here because it actually has negligible overhead and has overhead on par with stack cookies as they are used on the current system. But it offers strictly stronger protection than the current defense mechanism. And we are working on integrating that in mainline compilers. So to summarize, we've built a set of defense layers around our system that we can deploy one after the other, and they build on top of each other. So there's the safe stack that starts at the beginning, and in addition to that, we have code pointer separation and code pointer integrity if you want full protection. So how does the implementation look like? We have an LLVM-based prototype where we collect all the type information that we need in the front end in Clang. in the backend on top of LLVM, we have the safe stack, CPS, and CPI instrumentation passes, and we have additional runtime support in the runtime libraries for the safe heap and the stack management. The current instruction sets that we support are x64 and x86, and the systems that we support are Mac OS X, FreeBSD, and Linux. The current status of the implementation, we have great support for code pointer integrity on Mac OS X and FreeBSD for x64. The upstreaming of the patches is in progress, and the safe stack should be coming to LLVM soon, as soon as the patch goes through and we figure out the development process. You can fork it on GitHub now. If you want to look at the current prototype and play with it, go ahead and fork it. And the code review of CPS and CPI is in process, and we are working on it. You can play with the release prototype. We also have an image available, and we'll also release more packages soon. So the next question, I almost forgot to mention, some changes to super complex build systems are also needed. So when we were looking at FreeBSD, we obviously had to modify some of the make files of the FreeBSD package management and package compilation system. We did not have to modify any source code, just the build environment, to ensure that our runtime libraries are linked in as well, mostly. So you might ask, is it practical? Therefore, we recompiled the complete FreeBSD user space using our strong protection, and we successfully compiled it. And also more than 100 packages like Python, PostgreSQL, SQLite, and a whole bunch of other packages that are often attacked. So the defense that we are actually looking at has low overhead, is deployable in practice, and can be used today. So it is now your part to actually start playing with the system and get rid of all those bugs. Yeah.
So you motivate this work by showing the existence of all these exploits. So I wonder whether let's say, look at the last 2 years exploit on this target system. Are all of them protected using your mechanism, or there may be a few that slip through, or what's the situation?
So for CPI, we do have formal guarantees that no memory safety violation is possible. Therefore, all control flow hijack attacks are protected.
So, okay, so then are there other attacks that are not control flow hijack that sort of are in this CVE that consider serious, or?
That's a good question. Any data-only attack cannot be catched. So
I know it's theoretically possible, but are they really out there?
Imagine an FTP server that has an authenticated mode and a non-authenticated mode, and you have a bug in there. And if I can, as an attacker can write the is authenticated flag, our protection will not help against it. So this protection is only geared against to stop control flow hijack attacks.
I know, but I'm just wondering, in the real attacks, how many are this the control flow hijack, and how many?
That's the most common attack vector used today. So that's the biggest attack vector used. So in all the, we assume that given this defense mechanism, attackers will shift towards data attacks or data-only attacks as it gets harder or even impossible to carry out a control flow hijack attack. So in the future, attackers will resort to data-only attacks to either escalate their privileges by setting individual flags, like an isAdmin variable, or just extract the data as was done by Heartbleed. So for example, this approach would not stop Heartbleed. While there was a memory safety violation in Heartbleed, no code pointers were modified. Therefore, it would not protect against that. And obviously more protection will be, or more research will be needed. Like that. That's a good thing, right? So we can continue to look for strong defense mechanisms.
Like I said, we are in a field, you never need to be afraid of out of work.
Exactly, yeah, there's always more guarantees that you can give. And if you've given full guarantees, there's always performance you can optimize. So let me conclude. Code pointer integrity and code pointer separation offer strong protection against control flow hijack attacks. And the key insight that I want to to get through is that we are enforcing memory safety for code pointers only. Instead of enforcing memory safety for all the data that is out there, we restrict our protection to the data that is actually important and needs protection. We do have a working prototype that supports unmodified C and C++ and has low overhead in practice. The upstreaming of the patches is in progress, and the safe stack should be available soon. We do have a homepage out there, and you can focus on GitHub to look at the actual prototype. So, are there any questions? Thanks.